Good afternoon, all of you. So I'm thankful for you're here at my talk. I'm very sorry that I cannot be with you. I'm so regretfully double booked this week, so now I'm on a conference in Belgrade. So it has to be a recording. And I'm, by the way, Victor Ora Madsen, and I'm an ex-SLB advisor, now working as a consultant. So let's just get going to business, and let's talk about the subject matter. So I'm going to talk about fit-for-purpose data. How do we know if your seismic data is really good enough for imaging, or if it's actually fit for purpose for AVO inversion? So I'm going to propose to you a novel method for doing this, and I hope you will enjoy the ride. So just to be clear about this, imaging of the underground is very difficult. So that there are loads of challenges. You have acquisition challenges like uneven surface, you have scatterers, you have varying velocities, refractions, multiples, and you have attenuation, data loss. The Earth is a filter, so you're losing frequencies, and you have near surface effects like ground roll, and you have ambient noise. And all of this is coming on top of your seismic data. So that means that your data is compromised from the onset, and we apply various processes in order to remedy this and try to make the data more appropriate for both imaging purposes and also for AVO analysis and quantitative analysis. So here is just one example of data before conditioning and after conditioning. And we can study this a bit more in detail. So here we see three common midpoints, CMPs, which is kind of underground points as a function of offset. And the vertical axis is two-way time, and you can see this is more or less the raw gathers after a normal move-out correction or migration. So, but we can apply various processes in order to make it more appropriate, or in order to compensate for the effects of the acquisition and the underground and the noise sources. So here is just one example of the same data after conditioning. And in this case, you can see that there has been applied a mute in order to remove all the far offset data beyond critical angle, which we cannot properly image. And there has been some amplitude balancing in order to make sure that all offsets are in the same amplitude scale. And there are some attempts at spectral balancing and also a residual move-out correction in order to make the gathers more flat, meaning that the same reflector is at the same two-way time for all offsets or angles. So, and this is important in order to, say, in this case, do AVO analysis. So as you see here, this is one of the more popular kind of equations for AVO investigation. And it assumes that the reflectors are flat in the offset or angle domain, where we have, in this case, the intercept reflection coefficient and the gradient, which is a function of offset. And also you have the far offset gradient, which can all be inverted for in the case where the data is suitable. But in the case where it's not suitable, then one or all of these parameters will be noisy. So as I said, the fundamental assumption for AVO to work is that every angle offset seismic cube contains the same image of the underground. And the only variation between seismic offset traces for a given surface point is the amplitude and polarity of the reflected signal. But it's hard to satisfy in practice. So that is because, as you have seen, the seismic data might be compromised by many factors: poor illumination, ambient noise, near surface, heterogeneity, multiples, phase variations, and frequency loss. And the processing which tries to mitigate this depends on many complicated, ambiguous processing steps, which requires time-consuming application by experts. And these are experts. They are sometimes hard to come by, which is making it time-consuming and slow and expensive in order to apply it competently. So how do we know if the seismic data is fit for purpose when we have no well control? The experienced geophysicists, they have been flip-flopping between offsets and angle and stacks for ages in order to make some subjective statement about this image is better than that. So visual inspection is crude and sensitive to amplitude and polarity changes. So we would benefit from a reliable measurement of pre-stack imaging quality, which is insensitive to amplitude and phase. And it's objective as well. And if we can measure imaging quality, then we can use that as well in order to optimize the quality later. So my proposed solution is to use structural dips, because dips are amplitude independent, and that they are an expression of the seismic image. So what we want to ensure is that the seismic image is invariant across offsets, and that the only change is polarity and amplitude changes. And if it is not so, how can we quantify that deviation from our assumptions? So, and in this image, this is a time slice of an inline dip across seismic data west of Australia in the HCA dataset. And as you can see, that the dips are really expressing the structure of the underground very well, except in the fault zones, and where we don't really have any dips. And I would like to use the Volve public domain dataset as an example, which is kindly donated by Equinor to the public domain. And then the nice thing with Volve is that it is not only post-stack data, but it also contains pre-stack data, including the near, mid, and far offset angle stacks. So here we are looking at the inline dip down at the time slice going through the reservoir zone. And this is the inline dip for the full offset stack, which is presumably the best quality image of the underground. And you can see how the structure is in the underground at that particular two-way time. And we can compare that image with the image for each angle band stack. So this is the same time slice for the near stack, and we can flip-flop between them, and you can see that the image is somewhat different between the full stack and the near stack. And it is the same thing we see for the mid stack. The mid stack is different from the near stack. They are very similar in many cases, but there are also places where you have deviations or inconsistencies between the angle stacks. And this is the same for the far stack. And as you know, the far stack is the most hardest data to combine, but because the travel path for the rays or the waves propagating down to the layer and up, that they are the biggest trajectory or the travel distance. So it experiences a lot more noise and a lot more attenuation than the near and mid stacks. So anyway, there are, as you see, a lot of similarities between the mid and the far stack, but there are also deviations. So that's why I propose a new attribute called imaging quality, which is a space and time variant quality, which is calculating the deviation of the inline dip and cross-line dip from a reference dip. And in this case, the reference dip is the dip of the full stack cube, and then we compare the kind of full stack dip against the partial stack dips, and to see and quantify if there are any deviations. Yeah, that means in deviations in the sense that the partial stack has a dip which is far away from the consensus dip for that location. And obviously, in order to have a perfect stack or a data set for imaging, that you would like them all to be identical. So what we want to do is to exploit or examine where the dips are very different between the stacks. And then that means we are going back to the Equinor Volvo data set, and in order to investigate the imaging quality attribute for each angle band stack. So here is just a zoom in to the reservoir zone for the Volvo reservoir. And yeah, so this is the seismic amplitude for the full stack. And here is the similar amplitude inline amplitude map for the near stack. And we can kind of flip-flop between them. And visually, you see that there are a lot of similarities, but that there are also differences. So here is the imaging quality attribute for the near stack, and I have just drawn circles around the larger errors in the image compared to the reference dip, and this is highlighting where the near angle stack structure is very different from the reference structure, and we can overlay that with the seismic data, and we can do the same for the far offset stack. So here is the mid stack. Oh, sorry, they do the same for the mid stack, and here is the amplitude for the mid stack, and here is the imaging quality error for the mid stack, and I have just drawn circles around the events or the locations in time and space with the largest error. And in general, that there is a low error, but then there are some areas which stands out with a high degree of deviation of structure compared to the reference image. And we can do the same for the far stack. And in this case, as this is the far offset or angle, and the travel time is the travel distance for the seismic wave is the largest. It has experienced the most noise and attenuation, so it is also the hardest to imagine. So here is the imaging quality error for the far stack. And as you see, it is very busy. That there are only a few zones where you really have a low error, and that means that these are the only zones where you really can do an AVO analysis, which includes the far offset data. So here is another image of that, or just focusing on the areas with what we see in the background here is the full stack seismic data with the areas or zones where you have a high imaging quality error on the near stack, and you can compare that with the near stack image. And if you flip-flop, you see that it automatically highlights where you have a deviation in structure between the full stack and the near stack, which is indicating that in this case, the near stack is generally suitable for inversion, except in those areas within those circles. And we can do the same for the analysis or investigation for the mid stack or the mid angle stack. And here is the full stack image with this circles highlighting the areas where you have a high degree of uncertainty of imaging or imaging quality error in the mid stack, and you can compare that with the mid stack. And if you flip-flop, you see these are the areas where you have a fairly high degree of error in the mid stack compared to the full stack, and it's suggesting that you cannot trust the stack or the AVO analysis or the input from the mid stack in those areas. And we can finally go to the far stack, and again here we have the full stack data in the background, and with the highlighting the areas with high imaging error in the far stack, and you see that it's rather busy. That means that the far stack is in general difficult to use meaningfully in an AVO analysis workflow, except in this kind of focused area in the center towards the right. So and this is the far stack with the same circles, and you can, if we flip-flop, you can see that the images are very different. And you can appreciate that because the far offsets are, or far angles, they are so much harder to image than the near and mid stacks. So that leads me to the conclusions. We now have an objective imaging quality metric, which is insensitive to natural AVO variations, but at the same time is sensitive to natural AVO error sources. So this metric can be used to quantify local imaging quality, and we can now say on a sample level how much we can trust an imaging or an AVO inversion product. And again, if we can measure quality, then we can also use it as a minimizer. So meaning that we can do multiple kind of scenario parameter testing of the processing flow, and we can see how it improves the imaging quality objectively, and then we can choose the processing flow which minimizes the imaging error. And I hope you find that sensible, and I would in the end acknowledge that this work was done while I still worked at SLB, and SLB owns the property for the intellectual property for this method, and Petrel was used for the generation of the results which you see here. And I would again thank Equinor for releasing their VOLV seismic dataset, which is very useful for the scientific community for our endeavors. So I will by this thank you for your attention, and I'm very sorry again that I'm not able to be there with you and take your questions, and I hope that the chairman at the session will instead kind of make the best out of their Q&A time for after this talk. Thank you very much.